Okay. So today we start our second part on image processing. This subject has three parts. Number one is data structured processing of structured data. So we did some pandas and we did some looping over Excel-like type of data. So we had text data essentially, but that came in the form of some rows and columns, and we looked for information and processed information in there. That's for me not my main area of specialty, but that's where a surprising number of computer scientists and data scientists today still work. Many companies work with this type of data, and in many research projects you end up with at least some of the data being in that form. So I think it's always useful, and it's also easier to start with because you don't need so many software to start working. From now on, we will be working with images. And as you will see, we will need a little bit more software to work with images. Today, we will explain that in detail. We will explain what images are and how they are processed by the computer at a, let's say, lower level as matrices of pixels in this case. And we will also see how we can use them conveniently. This week, we will focus on basic tasks with images with OpenCV and how to visualize those images essentially with Matplotlib, which is another convenient library that we will use with Jupyter notebooks. This second project will take us 4 lessons. So the deadline, as you can see in web class, is, I think I can practice here. The deadline for the second project is June 17th. Okay, June 17th is today 1, 2, 3 more weeks. Okay, so 3 more weeks, and then you have the 1 extra day. Okay, to dedicate to this. From past experience, the contents in this second project are probably easier overall for many students, or they feel easier for many students, but they are also new. I think the contents themselves are actually quite a lot more complicated than project one, but many students feel that once they have reached the level they are confident with the code in project 1, then jumping up to the level of project 2 is not so difficult. But you will need to be confident with the code that we have already done, and looping and variables and functions and all of that good stuff in order to succeed here. Project 2 has many tasks. Today we will start seeing some, but you have project 2 already published, so you can check them yourself. Okay, let's see where we have project 2. Yes, so here we have project 2, and project 2 has 1, 2, I think it's, in the end I left that at what is it, 10 tasks. Okay, as in project 1, you don't need to solve them all to succeed at this project. You don't even need to solve them all to get 100 points in this project. Okay, but those tasks give you the opportunity to learn different things. If you are already a seasoned programmer and you already even have some experience with computer vision, the initial task especially will be very easy. So go ahead, forge ahead, try to learn about the other tasks too. And I think you can have some interesting content there for everyone, hopefully. Remember that you can and you should submit your work as early as possible, even if it's not finished, and I will give you feedback. So I think that's a way in which you can monitor your progress. Remember, deadlines are not extended except for very special circumstances, which do not happen often. So please try to submit as soon as you have completed a few tasks. If you have any problem, remember that you can ask. English is okay. Japanese is also okay. Absolutely no problem. Okay. We are trying to use as much English as we can in this lesson, but Japanese is super welcome. Really do not hesitate. If anyone feels that there is some part of the text of the exercise that's not super clear, we will provide the Japanese translation, and you can communicate with me, with Moritake too, in Japanese. His Japanese is way better than mine, but I will manage somehow, okay? Okay, I think that's about the introduction for the second part of the subject. The third part of the subject will be about deep learning. And we will be doing image analysis using deep learning. That part is a little bit more, it's a little bit different for beginners and for people who already know a lot about coding, because we need to learn about deep learning and what deep learning can do and what it cannot do, as well as how to code some deep learning. So that's a little bit steep for people who have no confidence with coding. So let's say that in the third part, the goals for beginners and the goals for advanced people are substantially different. Okay. In this second part, my goals for mostly everyone are similar. The main difference is that the people who are already good at coding will be faster, so they will be able to complete more of the tasks. But essentially, I am starting from the base that most contents will be new to everyone, that they will also not be difficult to acquire for most people. And I hope that we can progress as far as we can and learn something, like as much as we can in the process. Okay, I'm going to try to shut up. I'm speaking way too much already. So what we are going to do today is that we are going to the index. See if I can, yes, here I am. And we're going to be doing some contents from this course 4, Introduction to Computer Vision and Deep Learning. This set of courses started as a way for me to reflect what I was already explaining in my classes here at Yamagata University. I felt that I needed to provide some unified place for people to go and have access to the materials that I was explaining in different lessons. This thing grew, and this is turning into a kind of a specialization for Python for data science. There is quite a lot of content on programming, but okay, here I am back. Can you hear me again? I'm sadly having quite a lot of problems with my internet connection today. Okay, so we'll try to continue like this. If there are many problems like this one, where my internet connection just dropped, I will try to change the computer and hope that in the other one it's better. But I think it's a general problem with my connection in the office today. So we'll do our best. Please bear with me. I was saying that this set of courses, which I think you're still, no, I'm not sharing anymore. So let me share again. Okay, now you can see them again. So this set of courses that I have been working on were initially aimed at drone image processing, because that's part of a research project that I'm carrying on with the people at the Faculty of Agriculture in Yamagata University, and also with researchers from other universities, including, for some of you well-known people, from Torino University, for example. This is also growing, and I have started recently to gather some materials, and hopefully this will grow very soon, on Python coding and data science coding for document processing, for ancient Japanese processing. And what I want to tell you with this is that Python and data science can help in many, many research areas. All of these deep learning contents that we will see in the third part of the course were developed for medical imaging. And I'm also working in some project like that. Maybe one day I will also try to gather and compile a course in medical imaging here too. But for now, most of the contents that we will see in the second part are from this computer vision for drone image processing. So for forestry and recently agriculture applications too. But hopefully I will be able to show you some for the processing of documents. All of it is image processing, and we do most of that with very similar techniques: image classification, object detection, using the same code and the same networks, fine-tuned for different applications. No matter what your master's research is about, what you do later in life, probably you can use Python, and very likely you can use image processing and deep learning. So I hope to show you some examples. In Project 2 itself, most of the data is this Sarah's data that I will tell you about later, and it's about drone image processing. Okay, here we have some drone images that we will be processing. But then later, we also have these images. These images are from a graduation thesis project that we did a couple of years ago with people from the geology department. So these are images from a volcano, and we have some annotations, manual annotations that a student in geology in Yamagata University did. And then in task 10, I will ask you to process them too. So any type of image, it doesn't have to be drone images like the ones that we are seeing now. It can be scans of a document. It can be images taken by a self-driving car. All of those can be processed with the type of images that we will be seeing in the remainder of the subject. And this will be just an introduction. I hope to give you an idea of how to learn to use different techniques that the OpenCV library, the scikit-learn library, the Matplotlib library offer, but also to give you an idea of the goals and the current possibilities of deep learning networks and deep learning libraries like PyTorch that we will be using, so that then you can go and find the best code for your own projects and for your own work. Once again, do not fall into the ChatGPT trap here, okay? ChatGPT is particularly bad at this type of coding. This type of coding is slightly more complex. Some of the simple things it can do, it very easily will be confused and will end up creating code that's worthless. So especially now that you're learning, do not trust it. It's a useful tool sometimes. I'm saying ChatGPT, I mean any AI tool, okay? They can help with some simple things to make your coding a little bit faster, but if you have to rely on them teaching you anything, that's going to be very dangerous. I have a recent experience of a PhD student who was stuck 4 months trying to fix some image classification code, object detection code that ChatGPT had done for her. We started from scratch and had a working code from something that we had already from tutorials on the library she was using in 2 days. Do not trust these tools. Learn how to do things. Learn on your own. And then once you know, maybe you can use those, once you know what you're doing, as a way to speed up your coding. But do not try to learn coding with those, because at the moment they are really bad, and I'm not sure they will ever get better. And I will tell you about why I don't think they will get better in the third part of the subject. Okay, again, so we will be processing some of these notebooks. We will be seeing some of these notebooks today. I will be focusing on the first one about image basics, which is the main content that we have to see today. And I will show you a little bit about this global maxima for treetop detection notebook 2. Next week, we will be working with the NumPy for image manipulation one, okay? And that's the one that's a little bit trickier. That's the one that contains the most, let's say, difficult. They are not really difficult, but they are one jump in abstraction, okay? So they are a little bit more complicated. So if you already know everything that's in the image basics, you can go and have a look at this NumPy for image manipulation. And next week, we will be dealing with that quite a lot. Okay. So I'm now going to the first one, to the introduction to image basics, okay? So here, again, let me save a copy in Drive just in case. And just in case I want to change something so I don't mess up the main course content. Okay, yes, here I have it. We will start by downloading some data. This Incolab takes a little bit. Word to the wise, many of the, well, not many, all of the code that you need to do for this course can be done in Google Colab, in the free version of Google Colab. If you want to program these deep learning networks and some of the image processing for your own applications, you will probably need some computers with a little bit more computing power. You will probably need a computer with a GPU on your own, or to pay for Google Colab if you don't have any access for that, okay? I absolutely get no money from Google Colab. I think it's a system that works. I have used it sometimes, not a lot. If you're going to be doing lots of deep learning, it's generally cheaper to find a way to buy a computer with a GPU. But if you're only going to try, but need a little bit more computing power, that can be a way to go. There are other services similar, Paperspace, Amazon Web Services. There are many, many around. Okay. If you need more computing power than what Colab offers, for example, to run larger classification or object detection networks, I'm thinking about the latest transformer networks, about CompNext, about Swin, about some of the object detection networks, faster RCNN with one of the largest backbones, you're going to need a computer with a GPU. But to complete the materials of the course, you can do everything from the free version of Google Colab. And in that free version of Google Colab, as usual, we have connected to a distributed computer. And in this first cell, I have downloaded a couple of images. Okay, and I have them here. I clicked on the folder icon, and I have them in my distributed machine hard drive. Okay, one called circles.png and one called tanuki.jpg. Tanuki is the Japanese word for raccoon dog. Okay, I don't know what the word for that is in Italian. In Spanish, that's mapache. Okay, so now in that computer, we have our data, and we can start working with images, but maybe not so fast. First, we have to speak a little bit about environments and packages. So far, we have been working with some libraries that were installed by default. Okay, sometimes you might need to install additional libraries. Libraries are just collections of code that someone has done before. Okay. Okay, it's the other way around. Well, that doesn't matter. There are many collections of code, many code libraries for many different purposes, but we will be working with one library called PyTorch for the deep learning part of the course, of third part, and we will be working with OpenCV from today. We will also be seeing a little bit of scikit-learn and quite a lot of matplotlib that I haven't installed here. I haven't mentioned here. I recommend that if you work in your own computer, you use some data science type of processing software, like, for example, Anaconda. There are others, but Anaconda is the one that I recommend, and that you use programming environments. What are these environments? If you try to install the different libraries, and each application will likely have different versions of each library, OpenCV2, OpenCV3, usually now, different versions of Python, maybe an old application is still using Python 2. If you try to use the different versions of each library, the different versions of Python in a single system-wide installation, that can cause lots and lots and lots of problems. And every application that you do will likely have different versions of the library. So what we will try to do is use programming environments instead of installing in every version of the library in a different in the single system. We will try to make one kind of a bubble, one environment for each different application. That will allow us to encapsulate and have the different versions of each library separate from each other. And that will be the way to avoid the programming conflicts. Okay, so how does that translate to to our Colab notebooks? Basically, we might need to sometimes install some packages in Google Colab before we start working. Okay, so for example, I might want to install PyTorch. Okay. Okay, so I'm not using the correct let's see. I'm not using the correct syntax. Let's okay, PyTorch is a little bit complicated. Let's just go for trying to install OpenCV, for example. I'm going to be wanting to use OpenCV in my application today, in my code today, so I might want to just install it. Okay, so the computer that I now have has an operating system and has many things already installed. It has already many Python packages by default installed by the good people at Google for them to make my life a little bit easier. Okay, in this case, for example, I wanted to install OpenCV. I just Google how to install OpenCV with pip. Pip is one of these package managers and virtual environment managers. So pip is a program to install my code libraries inside of my virtual environment. Okay, so I simply made a code cell and wrote down a pip command, pip install OpenCV Python, and that would have helped me install my OpenCV library just here. What happened is that it's already there. Okay, let me just show you another example here. I do have another library for processing PDFs. Yes. Okay, so I can install this one here. I can, sorry, write down this one here. We'll get there eventually. Yes, here we are. I can now erase this one. Okay, so here I'm installing a different library. Okay, and now I managed to install it. This means that now the distributed computer from Google that has, as I said before, these two images in its hard drive, now it has also installed the PDF2 image library inside of its operating system. Google's distributed machine act also as my virtual environment, because every time I close those computers, any installation that I have done will also be erased. Okay, so if you see any of these pip things in your Jupyter Notebook code or in your Colab Notebook code, it means that we are going to use some library that's not installed by default in the Colab machines and that we want to install it anew. If you see those, you will have to run them every time that you run your notebooks in Colab. If you're working in your own machine and you download the notebooks and you create your own virtual environments using Anaconda, which is the way of working that I recommend, you will only need to install these libraries once per environment. So to sum up, we will be working with code libraries. We'll be showing you some code from the OpenCV library in 10 seconds. In order to work with those libraries, we need some environment where to install those libraries. For most of you, that will be transparent and you will not have to do anything. We'll just open Google Colab and those libraries will be there for you. If you download the notebooks and try to work in your computer, maybe because it has better hardware than the free Colab machines, or maybe because you're doing some application of your own later, you will need to take care of those virtual environments and of installing the libraries. And for that, I recommend using Anaconda to create environments and PEEP to install those libraries. Okay, plenty of tutorials around, and this is something that's not often covered in this kind of courses, but I have found out that people are often very confused about those things, okay? So I felt it important to mention them before we begin. Now, finally, after all this talking, let's go to the image basics. And first of all, we have to we have to define what an image is. And an image essentially is a collection of pixels. An image is, if we get a little bit philosophical, sorry, images are representations of reality. We live in a world that we perceive through our senses. And for us here, the sense that's important is sight, the capacity to see, to view things. And in that case, the light interacts with our eyes, and first with objects, and then it bounces and ends up in our eyes, where it's gathered and processed and shoehorned. It's used to create these models of our world. Some people have tried to represent objects or scenes from the world so that we can look at those representations and remember or get information as if we were looking at the original objects or the original scenes, okay? And that's what image processing does too. So for example, this is a very simple example of a nice image, and you have the source here, where someone has used points to represent color, to represent texture, and all of it to represent a whole scene, whole country or mountain scene, okay? In this case, by using many points with different colors, we can make an object that represents, that becomes a whole image. When we use computers to represent images, we do the exact same thing. One image is, one digital image is a matrix of pixels. Okay, a matrix is a 2D, 3D, 4D list of objects. And in this case, our objects are the pixels, are the same points of color that we could see in this kind of image. Okay, so for us, an image will be for us 2D representation of pixels. Okay, there are also 3D images, and we will not be working with them here. But for example, if you go to the doctor and you get an MRI scan of the brain, what they are doing is creating a 3D volume of your brain. To be super precise, that's not exactly 3D because it's like many 2D slices, but it's the next best thing. It's a 2D, 2.5D, 3D model of your brain. In this subject, we will be working with 2D images, with flat images. We will have X and Y, and in each position of this 2D matrix, we will have 1 pixel. Okay, so they are pixels. The points of color are placed in a regular grid, so they form a 2D matrix. Okay, first here I wanted to show you a little bit about matrices. So here we have a 3x3 random matrix. Here you have the way to generate it using NumPy random. So we are still using the NumPy library and many libraries that we were already using before. For example, here where we are using also this StimP new library to draw the matrices prettily. Okay, and for us, taking this idea of the matrix, of the 2-dimensional matrix, we will have representation of our images as matrices of pixels. For example, in this case, we will create a 2D matrix with 400 times 400 positions. Okay, and in each position, we will put something that will have 3 elements. So I will have a grid of 400 times 400 pixels, and in each position of that grid, I will have 3 values. Let me speak for a second about those 3 values. I was speaking a while back about my color points. Okay, the way that we most frequently represent color images is by using the RGB system. So we have 3 what are called channels, 3 channels of information: the red channel of information, the green channel of information, and the blue channel of information. RGB, red, green, blue. By putting all of those together, we create different colors that are not only red, green, and blue, but combination of those. So we have very clearly blue, so probably the red and green channels are close to 0 here, and the blue one is very high, but we also have all of the different combinations of colors. You can look at the color wheel to see how those combinations work. And we express those by having, for each pixel, 3 numbers: the red, green, and blue channels of information. So what I have been doing here is to create one image, like one digital image, like the one that I had before, at a 400 times 400 grid, and at each position of the grid, I have a color point. Which is all well and good, and not always the case. In the whole document processing things, we will use grayscale images. And in project 2, for the annotation, we will use also grayscale images that for us will mostly be binary. Grayscale images have 1 single channel, so each pixel is just 1 number, and it's grayscale. It's from 0, what means it's completely black, to 255, which is completely white, and all the possible shades of gray in between. So I have sometimes images with 3 channels, our regular color images that we take with our mobile phones or our cameras. And we will be using also grayscale images in our annotations. Binary images are basically grayscale images where I restrict the values, and I also only consider the 0 and the 255, or sometimes explain it as 0 and 1. And things are binary, so they are only either black or white. There are many, many, many more types of images. When we use our drones, we have sometimes multispectral images. So the drones that carry multispectral images take images on the RGB spectrum, so they have these 3 channels, but they also gather information on light that the human eye cannot see on the infrared, so lower bandwidth than the red, and the ultraviolet spectra. So spectra lights that exist that we cannot perceive with our eyes. So very easily I have, apart from the RGB, usually 2 or 4 more channels. So I end up with pixels that do not only have 1 to 3 numbers, but have usually 7, 9 of them. There are other cameras called hyperspectral that can see more bands of light, and those can have tens of thousands of channels. Sometimes those channels come from different types of information. Again, with drone image processing, we can very often reconstruct, along with the colors of the things that the drone is imaging, we can see the altitude with DSMs, DEMs, CHMs, all different types of names for maps that show what height is there at every particular pixel, how tall that is. That's often another channel. And there are many, many, many ways in different types of data to get more channels. We will be focusing here on either color or grayscale images, but everything that we do now and in the third project works exactly the same or very closely similarly in PyTorch with more channels. Okay. In case you're thinking of using this kind of deep learning code for your own application, and you do have more channels, please be advised that things like transfer learning and higher level libraries that give you models pre-trained and provide you with interfaces to just load your data and so on, those may not work so well with data that's not 3 channels or 1 channel. Okay, so from the point of view of the PyTorch library and the conceptual things that you can do with image processing and with deep learning processing, having more channels is really not a problem. Everything works exactly the same. If you really want to take advantage of the coding capacities of PyTorch, for example, you will need to work with PyTorch itself. Okay, so here we are going to use the matplotlib library that we have imported here. Okay, matplotlib import is a little bit weird. We do not import all the library, but only something called pyplot, which is the way to show images that the matplotlib library uses, and we are going to show it to use this mycolor image. Okay, mycolor image, I made a matrix with only zeros with this size. The size is 400 times 400 times 3. If I show that, I get 400 times 400 grid with only black pixels on it, because I put zeros in all of the possible values. So if I print one element of my matrix, I'm printing element 0, 0, I will get a list with 3 values, all of which are 0. If I print 300 and 235, I will also get 0, 0, 0. And if I print 300 and 435, I will get an out of bounds error because I only had 400 times 400. I have a matrix. I can access all its elements. Remember that these things start at 0 and end at length -1. So 400 is also still out of bounds. So this goes from 0 to 399 and contains all of 0, 0, 0 pixels. That's the general structure of my image, and I have created and shown my first digital image. Maybe not a very exciting one, but that can already help you with task 1 here. Okay. Task 1, well, it will not help you so much. You have to load it, but you will end up with something of that same structure. We'll see the loading in a second. We can now define a binary image of the same size. Okay. So I have copied the same code. So first I'm defining the color image, and now I'm also defining my binary image. The binary image is again a matrix of zeros, but now the size is not 400, 403, but 400, 401. Okay, because in each pixel I will have just one value, and if I show one of them, 125, 23, I always have just 1 0. Matrices are lists of pixels. So images are matrices of pixels. For us in 2 dimensions, they could be more, but for us they will be 2 dimensions. If they are color, they have 3 channels. They have 3 elements for every pixel. If they are binary images or grayscale images, they will have just 1 element for each pixel. Okay. Now let's just create one image, and that's not something that we are going to do frequently, but it's a nice way to finish understanding the structure of images. So I'm going to again create my color image in the same way. I can print the element if I want, but I actually don't want to do that. So let me get rid of this one. And now define the binary image, but most important, I'm going to use one function from the CV2 library. I also imported the CV2 library back up here. Okay, the CV2 library is the OpenCV library for image manipulation. That will make it much easier for us to work with images. So I'm importing it, I'm importing NumPy, and what I'm doing is calling a method called ellipse. That does what it says in the package. It draws an ellipse in an image. I have to give it my image, and I can look up how this CV2 ellipse function works by just Googling it. Okay, so let me show you, for example, the okay. Here, let me show you the result of Googling this. I have some helpful contents from different pages that explain a little bit how this works and what it does. And I have, most importantly, the official OpenCV documentation. So come and have a look at these pages if you ever want to use a new function from OpenCV and don't know exactly how to do it. And I would say use both. Sometimes it's nice to have a short example that just does something quick and helps me figure out more or less what the whole thing does. But the documentation is, the official documentation is where all the details are. So if you need to know how a parameter works and so on and so forth, that's the way to go. For example, for the ellipse function, I had an input-output array, which will be my matrix probably, and then the bulk, scalar, and so on. I get the whole information about what how my function works. Okay, sorry, that was C++. It's often better to get the Python keyword in. OpenCV has a Python and C++ version, so this is probably better. This is official documentation, and this is the Python. Okay, from the C++ page, you can also go to the OpenCV page, but it's a little bit annoying, so probably Google it and just add the Python keyword there. Okay, back to the notebook. I'm using this ellipse method. You can have a look at exactly how that works to draw an ellipse there, and this is in color 25500. Remember, red, green, and blue. So that will be a red ellipse. Okay. Okay. Then I'm also going to draw a rectangle using another function from OpenCV, and then I'm going to plot the whole. I do it here. I drew a red ellipse in the color image. I drew a rectangle in the binary image, and then I showed them with matplotlib. And here I have the two things. My images are matrices of pixels, and I can modify, I can create them, modify them. If I want to make them white instead of black, I could create zeros here. Sorry, instead of zeros, this could be ones. There is another NumPy function called ones. If I do that, I will have something that will look very similar, because now my values will all be ones instead of zeros. If I want it to look white, I have to multiply the whole thing by 255, and then I get a white background with the same red ellipse on my on my forefront. Okay, gray, yeah, no problem. Okay, I could also define different colors in the background here. Can I do something that's colored? I'm not sure if this will work, but my point here is that I can manipulate all of the okay, cannot multiply it, but I could go and change all of the values for my NP1s so that they are not all pixels that have the same elements everywhere, but I could change them one way. Okay. My point here is that we have created a matrix, we have played a little bit with these pixels, and we have even used some OpenCV functions to modify our image. Okay, images, matrices of pixels. OpenCV is a very convenient way to work with them, to modify them. And we have also been using a little bit matplotlib to show them. First, we saw just imshow to show just one single image, and here we have seen how to show two images side by side. We have to create something called axes and subplots, and then we have, in this case, subplots of dimensions 1 and 2, so 1 row and 2 columns, and then we can add and show something different in every one. Notice here that I have had to use this color map thing. If I don't, by default, Python tries to, matplotlib tries to identify everything as colors and does something, whatever it can. Okay, if I have something that's binary, I always want to indicate it, and then I have my binary representation. Okay, but the thing is that most of the time, when I'm working with images, I'm not creating them from scratch in this way. Sometimes I want to modify, so knowing these drawing functions can be helpful sometimes. Sometimes I will want to draw a rectangle around each object that I have automatically detected. Okay, so I will very likely end up using the CD2 rectangle with my image. So sometimes using these drawing functions from OpenCV for image modification is going to be very, very useful. But I'm usually not going to be creating my data using OpenCV. I'm going to be reading it from file. In the drone image processing courses, we get this is one video from the people at the forestry department. Let me get out the sound. And here we see the drone flying, okay? Flying very, very slowly. but it's flying over a place called Koiwa-Nojo in Morioka. Maybe we'll explain a little bit more about those. But I have a machine that's taking these images all the time. In the case of drone image processing, I will have also then a software called Metashade, usually, or Terra maybe, that will gather all of those images. Each frame of this video is one of those images, and we'll put them together in something called an orthomosaic. But I will start from some data that someone has already collected for me. For document image processing, I will start with some images that someone has already scanned for me. Okay, so I will have that data collected beforehand. I will not be making my data myself. So I will want to load the image from a file. Okay, we saw before that we have in our hard drive these two images. So let's load one. The way to load images with OpenCV is using this inbreed function. And this inbreed function, we could look it up, but let me just tell you that it works. Let me see, for example, this might be a way in which AI tools can help you a little bit. Load an image from a file using OpenCV. And now let's see if Gemini suggests some things. An image. Okay, it's not suggesting anything, but well, you can get some. I think I finally succeeded at killing the Gemini inputs from my notebooks, but usually in many situations you will get a suggestion for this, and probably the suggestion will look something like this. Okay, and ChatGPT can maybe help you with this kind of thing. Okay, so these simple tasks maybe are the ones that ChatGPT can help you with. But again, if you need the details and so on, probably you're better off going to the documentation or checking a notebook so you're sure that you understand what you're doing. In this case, I'm going to need the path, the place where the image is and its name, and I'm going to be needing a flag. In this case, my image is just here in my hard drive in my Google Colab computer, so my path is just the name of the image. If I had put it in here, then I would have needed something like sample data, or something like this. And then the name of the image. I could do that if I had stored the circles image inside of this folder, for example. Okay, you might need a longer path, longer directions on what your files are if your files are different in different places in your own folder. In this case, I just need the name, and I'm going to mention that this is a grayscale image. If I don't do that, Python will try to load as much information as it can from the data that I give it. Okay. For example, I don't remember at this moment what the default flag is. Okay. So let's go to the official Python OpenCV documentation, and let's see. Okay. And let's look for inbreed here. Okay, here we have the flags, and we have that the flag by default is color BGR. Okay, so if I don't say anything else, the flag by default is the color flag. Okay, so I'm going to, if I don't give it this flag that tells it that what it's reading is a grayscale image, it will try to read it as a color image. Okay, and now I can just print one of its pixels. Okay, pixel 00, or again 34, 12 are pixels with one channel. Okay, and both of those are black pixels. If I print 3020, which will be somewhere around here, it will be a white pixel. So 3412 or 00 were black, and 3012 is a white. And then I can show my image using matplotlib. Okay. We have a binary image in the sense that it only has black and white pixels, but to be fully precise, this is a grayscale image. Okay, I could also image grayscale values here. So 0 and 255, those are the only ones I have. But if I want to modify it and add values of 125 or any value in between, I will have those here as some shade of gray. Okay. For example, we can add a gray rectangle. We will have, for the rectangle, CV2 rectangle function, we'll have to enter a start and end point, and we can do that and draw a rectangle in our image. And we have given the rectangle color as 125, which draws this grayscale square here. Okay. Remember, all squares are also rectangles. If a rectangle has all of its four sides with the same length, then that rectangle is also called a square. Okay, square means 4 90-degree angles, and 4 equal sides. Rectangle is 4 90-degree angles, and the sides are equals 2 to 2. Okay, so now I can open a function that I had in my disk, in my hard drive, with imRate. Have to be careful of the path and have to be careful of the flag. Okay. Going back to task 1, you can already solve task 1 and 2. For task 2, you can use exactly what we have been using here. Take the path and use the grayscale flag. For task 1, where you have a color image, you will need some other flag. Okay. You can check it out, Google it, you can get it from here. I recommend probably the imRate color. Okay. Flag for color images. But again, you can just Google it and find out exactly how to do it. Okay, so we loaded our image, drew a gray rectangle in it, and now we can very simply show a sub-image. An image is a matrix of pixels. A sub-image is a sub-matrix of the same pixel. Okay, so in the same way that I could select things from my list, as we have been doing in the previous project, I can select parts of my matrices like this. So let me do this in 2 parts, which will be a little bit clearer. I will call this copied image. Copied image is just image point copy. Okay, image is the one that I have loaded before. Image is over here. Okay, image is the one, is a variable where I put the image that I have read from file. Okay, notice that this is very convenient, and we could have implemented it ourselves. Okay, this is just going to the disks, reading from one particular memory position indicated by this name, and then reading the consecutive positions of memory that are indicated also in the header of the file and that tell us how many pixels that one particular file has. That's not super complex programming. You could mostly do it, but it's very inconvenient, very annoying to have to deal with this small thing. What happens if the image is grayscale or if it's color? How does my operating system exactly store things in memory? How do I find this name in memory? That's why we use code libraries. Not to have to spend time in these things that are not our main focus. Okay, instead, someone at OpenCV already took care of all of those annoying details. And now when I want to load a file, I just called inbreed and OpenCV takes care of all of them. So I have done all of those things without having to worry about them. I have gone to the memory, checked how many bits of memory I have to read, exactly how to communicate them to my RAM memory, all of those low-level stuff. And I have ended up putting all of that in a matrix type of variable that I have called image. And now I'm going to just copy it using another, in this case, NumPy function called copy. This is going to go over all the elements in my matrix of pixels and make a copy each separately. And then that will allow me to modify my sub-image or my image if I want to, without having to destroy the original data. Not the one in the disk, that one is safe, but the image variable that I have read. Okay, so here I made a copy, and now I'm going to select a part of that copied image. What am I doing here? I have a list of lists, so a two-dimensional list, and I'm going to select pixels from 18 to 30, and from 18 to 30, both in Y and X. Let me go over that in a second. And now I can press play, and I just use the display function to show that for this part here, I have the following values. I'm also showing the same image, okay, the same sub-image. This part here contains the white inside, the black here, and the gray rectangle, okay? So I have everything here, the gray rectangle, the black inside, and the white from the circle, okay? If I come back here and I paint, where is that? Here, the rectangle, if instead of 125, I make it a lighter gray, so only 75. Sorry, 75 is closer to 0, it's closer to black, so it's not a lighter, it's a darker gray. And I show it here. Now I have 75 instead of 125. Okay, so I hope that gives you a very clear image of, image is not the right word here, very clear understanding of how images work as matrices of pixels. Okay, if this was the color image, I would be having 3 values inside of here, which will be a little bit unwieldy, a little bit annoying to look at. So that's why I chose the grayscale image in this case. Okay. Okay. So we have been doing quite a lot of reading and interpreting of grayscale images here. If I want to also check my Tanuki image, I'm going to be using inbreed again with the inbreed color flag. And now I'm going to have to stop in another technical thing. I said a second ago, Y and X, okay? Because sadly, OpenCV, which is very convenient for many things, is also very particular for some others. For some reason, instead of ordering everything like X and Y, like everyone does, they decided to call those Y and X. Why they decided to change the order of the variables, I honestly could not tell you. I really, really do not know. But that's something that happened at some point, and good people at OpenCV just stuck with that. OpenCV has some strange conventions. So if you ever find yourself wondering about, is it possible that these guys have ordered the X and Y the other way around? Yes, that happens. Not only that, we will see also that instead of working with RGB images like everyone does, the good people at OpenCV work with BGR. So when they read images, instead of reading them in red, green, and blue format, they read them at blue, green, and red. So the green is in the same place, but the red and the blue are inverted. Okay. So because of that, when I go to the Tanuki image and I just read it with a different flag, the favorite color one, that's one, okay? Then I can just show these two versions. If I just show the AMG version, the first one, the colors are inverted and weird. Remember, this is what the image looks like, okay? The image looks like not the first one that I'm showing AMG, but AMG2. This is because the colors in this image have been interpreted as BGR, so blue, green, and red instead of RGB. Then what I can do is that I can change them. This line is a little bit advanced, but what I'm doing here is pretty advanced slicing. Okay, what does this line do? I go through my list of elements. A matrix, an image is a list of lists, and I have my first component and my second component that I'm not going to touch. I'm just going to iterate over all the elements, and then I have the third one. The third one is the content, the pixels, and there I'm going to do this. I'm going to go from start to finish and invert the last one. I'm going to read them basically from end to start. Okay, start at 0, end at the end, and then go down. So I'm going to be reading the RGB as the BGR as RGB. BGR, if I read it from behind, it's RGB, and then I end up with an image with the colors in the same, in the, let's say, correct position, the position that we are used. Okay, and then I can show that with OpenCV, I can show the direct image with OpenCV. Remember, the flag by default is the color flag. Okay, so if I open with OpenCV ImShow, which is another way to show images, which is not Matplotlib, I get the correct image from the start. I don't need to change. If you open images with OpenCV and want to visualize with Matplotlib, you have to do this. You have to change the channels. Okay, so what have we done so far? We have been talking about the structure of images, matrices of pixels. We have mentioned that those pixels can have a different number of channels, 3 channels, 1 channel, 4 channels, 10,000 channels if we are working with multispectral images, sorry, hyperspectral images. For us, we will work mainly with color and grayscale images. Okay, grayscale images most often as binary masks that will either have the 0 or the 255 value. We'll see a few of them just in a second. And color images, which will be the main source of our data. We have also used some OpenCV functions. We have drawn an ellipse, we have drawn a rectangle. We have even shown how to modify the channels or modify the pixels in our data at very low level, okay, which in general we will not use. We have also seen how to create a sub image by slicing and choosing just a part of our image. You're going to need that for task 3, I believe. Okay, so just this notebook will give you a nice head start for the second project. Then there are many more functions that can be used and that OpenCV already has. And you can even make your own. For example, I just Googled how to rotate an image because that's something that sometimes you might want to do. And I got this function from the internet that's using something from OpenCV called get rotation matrix. If you have a center and an angle, one rotation matrix has one very particular shape. Google that, but basically that's the cosine and the sine of the angle in the higher quadrant, and then the translation vector that the center gives you. Not going to enter into that, but let's say that if you want to make a rotation, you have to stick with a certain format that OpenCV can create for you if you give it the center of your rotation and your angle. And then you can transform an image with a warp affine function, also from OpenCV. Okay. For those of you already familiar with, for example, object-oriented programming and saying function all the time, I should probably say method. And those that are not familiar, you don't need to worry about that at all. What I'm doing here is I'm, again, reading the circles image, and I'm rotating it using this function. Okay, I can incorporate OpenCV functions in my code for many purposes. And in this case, for example, for rotating. I have to be aware of what it is that I'm doing, because I can run into trouble. If I do it like this, I get a really nice looking 90-degree rotation. If I do it like this, I get something that's cut. Oh, what happened there? Well, essentially, if I'm rotating around the center and I'm not careful, I might end up with a part of the image outside of the image that I have defined. Okay, so if you're ever doing rotations, remember that most of the time you need to expand to copy this into a larger image with some padding and then rotating that. Okay, not something that you have to worry too much about today. Let me have a look at the start of project number 2, and hopefully until 10:20, which is the correct time to end the class, I can also have a look at some of the local minima example, some of these other example too. Okay. So I think I already mentioned this in last class, but basically I have tried to make gradation of the difficulty of the exercises. So they have, of the tasks, sorry. They have a D1, D2, D3. For example, task 1 is very much, sorry, not task 1. They are group tasks. So basic image manipulations, which are task 1, 2, task 1 and 2 are just D1. Simple mass manipulation are also D1. Okay, D1 means everyone should be able to do this. Okay, maybe beginners it will take a little longer for them, but should not be too long. And people already familiar with programming should breathe through this. Difficult 2 should be doable for beginners still. Okay, not too difficult. Maybe a little challenging. Maybe you will need to try more than once, maybe ask for help, okay? And should still be relatively easy for advanced students. And then difficulty 3 can be significantly challenging for beginners. I wrote down, do not be afraid. Significantly challenging is not a bad thing. It's basically just a warning sign, okay? So do not worry too much if you're doing something that's marked as difficulty 3 and you're struggling. That's probably the point, okay? That doesn't mean that you cannot do it. Try. Maybe it's easier than I thought. Maybe you're learning really, really fast. If you get stuck there, do not beat yourself up, okay? And you can always ask for help. Difficulty 3, completing them perfectly can even be challenging for advanced students. So again, even if you're already good at coding and you cannot, for the life of you, solve some of the difficulty 3 tasks, again, ask and we can do them. Not exactly that, but I can provide some help at the very least. Okay. For the second project, we're going to be using Matplotlib as we have been doing. We are going to be needing time it because I'm going to ask for some time considerations regarding different ways to do things. OpenCV, OS, a library to manage files in general, NumPy, Pandas, and we can use defaultic and regular expressions maybe. Okay, you have already seen all of those. CV2 and Matplotlib are new from today, but all the others you have already seen. Maybe not so much OS, but a little. As usual, we start by downloading our data, and that's what I'm going to spend the most time with today. The data in this case is pretty large, and while it downloads, I will just briefly tell you why it's called Sarah's data. It's called Sarah's data because of this person. This is Sarah, used to be Sarah Kentz when she worked with us during her PhD at Yamagata. I think she finished in 2022 probably, okay? Or 2021 maybe, because I read here that she has been in Fraunhofer since 2022. So she did her PhD at the forestry group, and she worked with both Lopez Sensei and with me in some drone image projects. And she was a very good PhD student. And one of the things that she did was prepare this data that you're going to be using for this project. So this is research level data, challenging one, and that will also give you an idea of the necessities of working with this type of data, the importance of annotations, the difficulties of annotation, and so on. This data Sarah is downloaded as a zip file and then uncompressed in this cell. You don't have to worry about any of that. But that's the structure that it has. It's one folder called Data Sarah, and then it has 13 subfolders, one for each data collection site. Okay, all of this is extracted here, and we can use the list_dir function from the OS library to show that the Data Sarah folder has all of those subfolders. One for site 1, site 2, site 3, site 4, etc. until site 13. 5, 6, 7, 8, 9, 10, 11, 12, and 13. Yes, all sites from 1 to 13. 13 sites in total. Okay. This was something that I could not refrain myself from including. This is a class that shows all of the library path, so all of the data path in a text way. Okay, so if you're a beginner and you're confused by this thing, property, the class method, the class words, don't worry. But what this does is basically creates this text representation of the shape of the data set. Okay, so I can use the collab display to essentially obtain the same thing, or I can use that very simple Python code, well, not so simple, but not too long Python code to do the same. So if you're interested in how files are managed and so on, you have this here. And you have the source too. Okay. In any case, what was most interesting for me was to have a look at what the data looks like. And that's what the data looks like. Every folder has many files inside of it. Every folder corresponds to one site where we acquire data, and every site has the same structure. Okay. You have the detailed explanation here, but very quickly. Site 1, for example, has, first of all, I don't know if I can visualize it here, or if it's too big, has one ortho mosaic. So this is the image that you have to visualize. Yes, I cannot. Yes, I can open it. I can open it here with the Colab interface itself, but it's one of these images. These images are the ones that I said before are made by putting together many images taken by the drone. The drone flies over and over, back and forth over a large part of a forest. This is a forest in Yonezawa. And then those images are stitched together to build an orthomosaic. The good thing of the orthomosaic is that first, it images a large area of the forest, and second, it has very high resolution. Okay, I can show that. Let me see here. I cannot do that in Colab, but I can do it in my own computer. This is my operating system, and I have these same folders and file structures and so on, and I can open S1 JPEG, sorry, with GIMP. And then I will be able to show the same image, and I will be able to zoom in on it confidently. Okay. While this is loading, apart from the mosaic, I have many binary masks. Okay, that show me this is the orthomosaic. Okay, and I can zoom into it as much as I want, and I can see individual trees. And even though the resolution is not super, it's still pretty good. About 1 centimeter per pixel, I can get to see more or less the texture of the leaves. So I have data that images a very large area with very high level of detail. Not only that, I have also those layers that show me where each of the species are. For example, this is site 1, this is 2. And this is a binary mask of the same size as the orthomosaic. I can, for example, show it with a lower level of opacity. And I can see that this is showing me the position of species 2 in this particular site. So this is a tree of species 2. This is another one. These trees are not of species 2. Okay. And that's the main structure of my data. My mosaic, all of the masks that also always have the same name structure, site, in this case 1, the number of the site, species 01, 02. There are 44 different species that are not always present in every site. And with that, I have the information of the position of the trees, manual information. I will tell you a little bit more about how these annotations were done next time. Finally, I also have ROI, region of interest file. That's black for the part that's inside of the region of interest. Some of this mosaic is not interesting for us. The ROI tells me what's interesting and what's not. And then the treetops. Okay, let me show you that too, but that's only GIMP that just shows. Let me open it as a layer tool. Where is it? Bit of y. This just shows me the position of the trees with one small black circle marking the position of every tree. So there are all of these trees around, and these in particular are trees of species 2 inside 1. Okay, so the treetops file is another binary mask with the position of the treetops. Sum up information, mosaic, the species masks, where the location of the different species in these sites are. Not all species are in all sites, and then the ROI and the tree tops. One small black circle to indicate where every tree is. And that's what we are going to be processing. Task 1, you just need to load an image using OpenCV, and it's a color one. So go and choose hybrid and the correct black. This one is easy. We have done it already. Binary mask. So, okay. In task 3, you're going to be doing basic mask statistics. Okay, this is a little bit more challenging, but should not be too bad. Use a simple for loop, and using the way we have been using to access some of our pixels. We have been breaking pixels here. Okay, you can immediately know how to use a for loop to see if the pixels in one of the masks are black or not. Remember, black is value 0. You can do the same with a map. Map in this case, a little bit tricky to use. Okay, so this is marked as D1, 2, but this part with the map is a little bit more challenging. So don't worry too much if that is a little bit difficult. Probably you need something called a product to transform the image into something that you can iterate easily with a map. Okay, and finally, viewing the image as a NumPy array. We will be talking about that next week. Okay, and then we're going to be going with large-scale data manipulation. And that's what we are going to be doing in task 4. This is going to be the main task for this exercise. Okay, it's a little bit of a long one, but it will help us interpret all of that information in a convenient way. I've started the function a little bit, and I would like you to complete it. Once this is done, everything is downhill from there. We can do a data sanity check because the annotations have errors. We saw that with the data from project 1, and we'll also be seeing that too. Okay, then we can do some statistics and using our collected data with pandas and so on and so forth. Let me finish it here, and next week we will talk about images as NumPy vectors, and we will talk a little bit more about these other tasks too. Thank you very much for listening.